now. All right. So welcome to this last session in the operating systems course for this spring, and most probably my last session in the operating systems course at NTNU, unless NTNU has some very convincing arguments. Probably not. We handed out the example exam before Easter, and I hope you had a bit of relaxing time over Easter and didn't spend all the time like working on the assignments and learning stuff for the exams, but could also enjoy your time a bit. Nevertheless, I promise to obviously present you some of our example proposed solutions for our example exam questions. And of course, you can assume that the final exam will be similar-ish. Well, first regarding the type of questions, obviously, but also regarding the amount of questions. So that's why it's very useful to work through this exam yourself, because then you can figure out how much time you would need to work on that stuff. And that's really helpful because you're less stressed when writing the actual exam afterwards. So let's just directly jump in, I'd say, if I press the right button here. So we started with processes, and this is a typical question asking you about your understanding of a given piece of code using operating system functionality. And in this case, it's forking several times. So these 8 lines of code on the right-hand side do some forks. And so you should know what happens when a fork is executed. So when a process continues running, and also what the return value of a fork system call is, so 0 or not 0. And all these things are relevant here. So we have a fork in line 3, returning a first process ID number. And then we have another fork in line 4. And after line 3, and we say here, assume that all fork calls succeed. We already have 2 processes. So these 2 processes both continue after line 3. So they'll start executing line 4. So both processes fork. And then we have a special condition. So only if the return value of the second fork is 0 and the return value of the first fork is greater than 0, then we do some more forks. So the question was here to give the total number of processes that result from executing this code, including this process we started all of this with, and you should explain your solution. So overall, we are creating 6 processes here. So imagine we have the initial process that executes the code from the beginning, from line 1. And let's just imagine it has process ID 100. Then, as I said, it generates one child process using the fork in line 3. So after executing line 3, we have the original process with process ID 100 and the child process. Let's just assume for simplicity, it has a process ID of 101. So after executing line 3, we have 2 processes. So fork returns twice, once in the child process, once in the parent process, and the difference between child and parent process is the return value of fork. So for the child process, fork returns 0 always, because the child process can easily find out its own process ID by using getPit. And for the parent process, fork returns the process ID of the child that was just generated using fork, or if it didn't work out, it returns an error value. Well, we told you that you should assume that all forks calls succeed, so you can ignore errors here. So what happens is we currently have 2 processes that start to execute line 4. So after a fork, you return exactly to the position in code where you called the fork. So fork doesn't work by re-executing the child process from the beginning, but really continuing where the original parent process left off. So we have 2 processes now, process IDs 100 and 101, both executing a fork system call in line 4. And these are completely independent processes now, just having these parent-child relationships. So they both generate a child process here. So after fork returns in line 4, both in process ID 100 and 101, we have 2 additional child processes, because the original parent and the first child process both forked and generated 1 more child process. So we have 4 overall, and let's assume these child processes on this level have process IDs 102 and 103. Now, the interesting stuff happens, so we're checking for the return value. So line 5 checks for the value returned from the first and second fork call. So remember, we're only returned a value not equal to 0, so greater than 0, when we're in the parent process. So only if we're in the parent process that has executed the fork call in line 3, and we're the child process in line 4. Only then this if condition is actually valid and true, and then we can continue. So only if the first fork returned a value of larger than 0, and the second fork, that's a typo on the slide, returned a value equals to 0. So essentially we're the child process here, right? Then the code in lines 6 to 7 is executed. So altogether, we then have 6 processes. Right. Then we had another example, and there it was interesting to look at another property of fork, which is the execution order of processes, essentially. So we have this example program here, and the question is, this example program outputs some stuff. So we defined a macro here, which is a bit unusual because it uses this #x notation, but we explained it in the original question. I just took it out here because it didn't fit the slide. So we define a macro w of x, which writes to file descriptor 1, which is standard out, the character as a string that is defined by the x we pass to the macro, and then we pass the size of the macro. So we indicate how many characters this string has. So whenever we call w of a or b or c, we just print a string a, b, or c. So the question is, which outputs are actually possible by this program? Now, if you look at that program, the first thing that happens in main is we execute w of a. So in any case, the first character that's always outputted is an a, because we're not running any parallel processes here at the moment. Then in the next line, we fork and get, the process ID of the child back. Now, after this line with a fork, we have 2 processes, a parent process and a child process. So what can happen now is the order changes. So for fork, it's not defined in Unix if after returning from fork, the parent or the child process continue executing first. So what could happen is that the parent process executes first or the child process executes first. Now, if you look at what happens after the fork, both in the parent and child process, a b is output. So the second character is always a b, but now something can happen. Now, if child, so if we are the parent process, so child is not equal to 0, then we are waiting for the termination of a child process and outputting c. So depending on which process comes first, now we might have the child process first, which has a child value of 0, so it doesn't execute wait. So we would have a w of c executed, so we would output a, b, c. And then our parent process could start, we could have another bc, or we could have the other order, a, b, b, c, c, both would work. So here it was really important to know that the execution order isn't fixed, and parent or child process could come first here. All right, so that was a bit to think about, a bit of a logical puzzle, more or less, which required you to understand what's going on inside the Unix process model and what's happening. But I don't think it was too difficult, but it takes some time to think about it. So that's why I recommend to really work on the example exam exercises yourself, just because you can figure out how long it takes you to really think through the questions and the possible answers. All right, so let's go on. System calls is the next thing. So we have a system call parameters, and we gave a system call here, which is a read system call. You've probably all used this, which reads a number of bytes given by the third parameter count from a file, which is indicated by the file descriptor in the first parameter, and it writes the data that it reads from that file into a buffer, and the pointer to the start of that buffer is passed in a void pointer, so a generic pointer, to a memory area that you should have allocated before, because if you didn't, well, you just overread arbitrary memory and probably crash your system. So to enable safe and secure operation of the operating system, the OS has to check some properties of parameters to read. And you are asked to describe which parameter properties the OS should check before it would actually perform the actual read action from the file. And you were able to assume that buff did have a value that's not equal to 0 or null, and that we had a count that's at least 0. And we also allowed that page faults could happen after the check. So what does the operating system need to check? First, when you access a file, it needs to check the file descriptor. So first it needs to check if it's actually a valid file descriptor. And then it needs to check if this file descriptor is open, or to be exactly precise, it's open for reading a file, because you can have file descriptors that might only be open for writing, and then you would get an error. So the other thing is buff. Buff has to be a valid pointer in the user address space, and that's very important here. So if we would allow to pass an arbitrary value of buff and would not check the value of buff, then we'd have a problem here, because the kernel in general is allowed to write every virtual address in the whole address space. So it could write an address that's not mapped and would cause a kernel a page fault itself, which would maybe be problematic. So we said they're allowed to take place after the checks, but that's still a problem here, right? And the worst thing is there is a valid mapping that points to a completely different process in kernel memory. So the kernel might write to memory outside of the address space of the process that executes read. So what the kernel has to do when executing a system call like read is it has to check if this address of the buffer that's passed is actually an address that's inside of the virtual address space of the process that's calling it. So if there is a valid virtual address mapping, and also because this can be larger than one page, it should check that the count, so the number of bytes we rewrite, so the whole memory from starting the buffer at buff to buff plus count minus 1, that all of this is in the address space. So common errors, because these are some questions from last year's exams, so we can give you common errors for this, is stating that FD is larger than 0. Not necessarily. 0 can be a valid file descriptor, though it's usually standard in. But you can reassign it to whatever you like, so you can have a valid file descriptor 0. Stating that count is larger or equal to 0. Well, that's always given because size t is an unsigned type. Or some errors were leaving out parameters to check. Or some students actually gave an answer that the operating system should check that the size of the buffer is actually big enough. That's something you cannot do because you just pass a pointer. This pointer has no information on how big this buffer actually is. So this is a very complex question. So this took some thinking and probably confused quite a number of students last year. So that's why you put it in the example exam and not in the final exam. Right. Another question was about the Unix shell. And since you all implemented your own Unix shell now, you should probably know this. So when you enter a command in the Unix shell, you can either have internal or external commands. And here we were considering the change directory command in the shell. So change directory obviously is supposed to change the current path the shell is operating in, so the current working directory of the shell, to another directory. And the question is, can cd be implemented as an external command, so as an external binary that can just be called like ls or copy or something like that, and work as expected? That's the important part. So it should be able to change the path of the shell that is executing it. If yes, you should explain how to implement it. And if no, you should explain why not. So to change a directory, in a Unix process, you use the chdir system call. So you could write an external CD program, and that might look like this one line of code. As often here, we omit the includes and argument checks. So essentially, we just pass one parameter, argv of 1, to our program on the command line, so using execl, for example, and then we just execute chdir of this string argv of 1. Usually you should check that there's a valid string, that it's not null, and so on. But just let's just ignore this for a moment. So this is a perfectly valid program. If we add the includes and stuff like that, that actually changes the directory. Now, where's the problem? The problem is that each process in Unix has its own current or working directory. So when we execute this chdir and an external command, this is only valid for the external command. So it changes the path for the external command, and then the external command immediately terminates. So this information is gone. Could we somehow pass this information or this path back to the shell? Well, for this, we will need at least some sort of shared memory and probably some other features. So this doesn't work because the shell first forks. So it creates a copy of the address space with copy on write. So whenever we modify something in the child, it's not reflected in the parent process. And then it executes our cd external command, our hypothetical one. So essentially, there would need to be a way to pass this information back to the original shell. And there isn't, because these processes don't have any shared memory anymore. So cd, this external cd command, can change a directory, but it cannot change the directory of the shell that called it. So that's exactly the problem here. So it doesn't work. And yeah, essentially people have tried, and that's why you have to use cd as an internal command and just use the chdir inside of your shell implementation. The next question was about synchronization, of course, an important part of operating systems, just because we have parallel processes that access shared resources. And we have these three functions, F1, 2, and 3. And we assume they would run in separate threads each and print, well, some prime numbers. So we have 2, 3, 5, 7, not 9, but 11. And the blue lines were missing, so we had just comments there, sync, that indicated that you might want to include a synchronization operation using semaphores here, and we had 3 semaphores defined, and the initial values were also not defined for the semaphores. So your task was to actually run these 3 threads, F1, 2, and 3 in parallel, and synchronize them in a way that it outputs the end output would be the prime numbers exactly in the numerical order. So 2, 3, 5, 7, 11, and 13 exactly. So there's several options possible here. So we're showing one here. So the first thing you could do is you could, let's see, wait for S1 and F1. Why do we wait for something? Because F1 outputs a 3 first. 3 is not the first prime number, so we have to wait for something. Same with F3, because the first thing it outputs is a 7, so we have to wait for something else. And so let's now look which of our threads prints the first prime number, that's F2. So F2 starts printing a 2. So that's the first prime number, we can print it right away. So we wouldn't need a sync operation. We could also use a sync operation on a semaphore and initialize that semaphore to 1. That would also be possible, but it's not needed here. Both would be valid solutions. So after we printed the 2 in F2, we need to start the process printing the 3. So F1 is our thread printing the 3. So this waits for a semaphore 1. This is 0, so it's waiting. So now we need to signal it. So it's increased to 1, incremented to 1. So after signal as 1, well, F1 starts to run after the wait. So it prints a 3. And then it immediately can print the next prime number, because 3 and 5 are 2 subsequent prime numbers. So we don't need a synchronization operation in between there. And then we need something to continue with the 7. The other thing we need to do in F2 is we need to stop F2 from printing 13 immediately after it signals as 1. So we need to insert a wait after the signal in F2. So the rest works almost the same. So now we have to enable F3 to start. So F3 was waiting for S3. So in F1, we signal S3. So we have printed 2, 3, and 5 so far. Now F3 can start and can print 7 and 11. And then we can finally signal S2, which then enables F2 to continue printing 13. So there's a question, basically just use signal and wait to redirect the control flow, kind of like an error from the signal call to the wait call with the same value. Yes, you can draw errors there from wait to signal and the other way around. And that's exactly what's happening here. That's not a lot of magic happening here. So that's essentially all. There's no tricks involved. It's just really logical thinking and getting your semaphores and initial values right. So we initialize all semaphores to 0 here because we signal them by hand, so using code. And the first process, F2, the first thread, can start right away without syncing, or we could use another semaphore, initialize to 1 of the semaphores, and sync for that at the beginning of F2. That would have also worked, but it's not necessary. So common errors here. So of course we gave partial credits for partially correct orders of the output here. So it's not all or nothing, because that would be unfair if you make a little mistake somewhere. So common errors here were obviously incorrect orders, or especially the incorrect init of semaphores, or and that's a very common error I've seen last year, is that this wait for S2 was forgotten in F2. So we signaled correctly, but then both F2 and F1 would continue running. So we would have some arbitrary 13 printed between 3 and 5 or something, which is obviously not the right order. So this is just going by the book, by the definition of semaphores. It's not a trick question. Okay, another question was about semaphore implementation. And the question was if it's possible to implement concurrency primitives such as mutexes on a current modern multi-core CPU without using special instructions such as exchange or test and set and whatever we've seen. So in other words, can we write these concurrency primitives purely in C on current multi-core processors? Now, last year we had some trick answers from people who, well, it's not trick answers. We had answers from people who read their C standard, but didn't really read what's behind it. So in modern C implementations, and I think I need to mention it here, you have built-in so-called intrinsics. These built-in intrinsics look like the regular C code, but they map to whatever is available, for example, to implement atomic instructions. So there's underline, atomic something available in GCC, for example. And what this does is, depending on the machine you're running this on, like an Intel processor would use exchange, or a Motorola 68K would use test and set, it still uses the machine instructions under the hood. So even though it looks like C code, still it relies on these instructions because that's not standard C. So some students proposed algorithms such as a bakery algorithm here. That's perfectly fine. It's in general correct. And you would have gotten full credit when you mentioned that. But you should mention that these algorithms are problematic on multi-cores. And maybe one of the reasons for it we mentioned in the course. Some of you mentioned the problems with cache hierarchies and cache synchronizations. That's okay. That's fine. And some of you only mentioned the atomicity of instructions itself. Now that's a thing. If you have an atomic instruction, the instruction itself can be atomic as it wants. The problem is that this instruction on a multi-core processor is only observed atomically on this processor itself. What you really need is an atomic instruction that is an atomic instruction on the bus level. So it stops all the other processors. which might just in the same microsecond, nanosecond, whatever, try to execute a synchronization operation. So it needs to stop the bus system here, the bus transaction related to an atomic transaction instruction, because another core can execute the exact same instruction at the same time. So that's essentially problematic. This required a bit of understanding of computer architecture. So I wasn't too sure if this was going over the head of some of the students last year. So essentially, this is just an example question for you to think about how stuff works and what happens. But we've also learned you won't receive a question that relies too much on computer architecture, because we cannot assume that you have the required background here. So that was confusing some students, but most of the students nevertheless got an answer that was mostly correct here. What else did we have? Deterministic process execution, I think. So we have an integer variable x in a C program, and we have an instruction x++, and this is executed by 2 threads of a program in parallel. And what you do is you observe the value of x++ after the additions have occurred, and you are supposed to explain why in some cases the variable is incremented only once by 1, instead of as we would have expected it by 2. So obviously we would assume that x would be the same variable here. And this required you to understand that x++, though it looks like it's just a single undivisible instruction, it's not. So usually x++ on something like an integer variable is commonly translated into separate parts. For example, you would first read the memory at the address where x is stored. So that's the first line here. Store it in a register, which we call temp here. So just a temporary variable here. Then you would increment the value in that register. And finally, in step 3, you would write this incremented value back at the address in memory where x is stored. So x++ is not atomic here. And what can happen is that the first thread executes read memory. So it gets the original value of x back. Let's say it's 1. Then we have a process or thread switch to the second thread, which also executes the first line. So it also reads 1 because we haven't incremented it yet. And then we switch back. Both increment their value 1 by 1. So they end up at 2. And both write it back. So the first thread writes back a 2, and the second thread also writes back a 2. So instead of 2 increments, we only have 1 increment because both read the first initial value of that variable x into the temp variable. And this is, of course, a situation that occurs probably very rarely. So this is a typical race condition. So in most cases, it works fine. And finding bugs like this is pretty horrible. And of course, we gave partial credits here for partially correct answers. So for example, if you had an incorrect or missing indication when a context would be switched. So the context switch would be the important thing to mention here, that there's some switch happening between some of the instructions here, between the threads, that causes the incorrect value to be generated in the end. What else did we have? Synchronization is always a nice topic. So we had a bit more, this time about deadlocks. So we had this piece of code on the right-hand side here with 3 threads. So the first one executes some weights and signals, the second one also, and the third one also. And initially, you should assume that all 3 mutexes are initialized to be not locked. And you should also assume that the threads can execute in any arbitrary order and interleaving. So whenever between the lines of wait and signal in all of the threads, or between 2 waits and 2 signals, there could be a thread switch. And the question was, can there be a problem when executing this multi-threaded code? If yes, you should show an interleaving that results in the problem. And if no, you should explain why not. And what can happen is that there can be a deadlock. So consider we start with thread 1, which executes wait for L1. So it waits for L1. Then we switch to thread 3, which starts waiting for L3. And then we switch to thread 3 finally, which waits for L2. So now we have this circular waiting condition in our yeah, essentially process dependency graph that we could draw. We don't have to draw it here. And this would mean none of the processes could continue running here because none of the processes would be able to signal any of the semaphores to enable one of the other threads to continue. So we have a circular waiting condition here as indicated in the last line of our slides. So the second part of the question was, if there is a problem, propose a fix. Well, obviously that gave a hint that there should be a problem because otherwise you would get 5 points for free. And the solution for this would be, for example, to acquire locks in different order, for example, L1, L2, L3, and then it should work. Right. What else did we have? Memory allocation. So buddy algorithm is one of the things we looked at in more detail here. So we have a typical example for buddy allocation or memory allocation with a buddy algorithm. So we have a system with a memory of 32 megabytes and 4 processes that request memory one after the other in the order A, B, C, D. And you should use the buddy algorithm to perform dynamic memory allocation. And the following allocations that we are given here take place in the given order. And we already indicated the first one in the table, which is on the next slide here. So we have a process allocation A of 6 megabytes, a process allocation B then of 9 megabytes, process C allocates 1 megabyte, and finally process D allocates 6 megabytes. And if one of these memory allocations cannot be fulfilled, you should indicate this. So we always have to use like powers of 2, that's the thing. And we had, and that's something you had to read from the table, we had always memory blocks you could allocate of the size of 2 megabytes. So we had 16 2 megabyte blocks, making our 32 megabytes. And our first process allocation was already given. It allocates 6 megabytes. So we need to round it up to the next power of 2. So it needs 8 megabytes. So it allocates the first 4 2 megabyte slots here. Then process B in step 2 allocates 9 megabytes. So 9 megabytes is obviously larger than 8 megabytes. So we need a power of 2 size block that's larger than 9 megabytes. So we need a 16 megabyte block. And these 16 megabyte blocks have to be what we call naturally aligned. So it has to be starting at an address that's divisible by 16 megabytes. So we only have one place to put it, which is the blue axis on the right-hand side for process B. So from 16 to 30, because it has to be aligned on some address, starting address divisible by 16. All right. Now process C allocates a single megabyte. So we need a 2 megabyte block for this because we need to round it up to the next, to the minimum block size. Here, so we could allocate it to block 8, but we could also allocate it to 10, 12, or 14, but all would work. Now process D allocates 6 megabytes. And here we have this situation with the buddy algorithm that we have 6 free megabytes, but we can't allocate them because we need to round up these 6 megabytes to the next power of 2, which is 8 megabytes. And there is no free 8 megabyte block left here anymore. So the allocation 4 for process D is not possible. So even though we have 6 megabytes free here, we can't fulfill this because then our buddy algorithm would not continue to work. So that was just the buddy algorithm, more or less by the book. Nothing special here. The second memory allocation was about the LRU algorithm, so least recently used. So we have a system with page addressing and LRU page replacement strategy, and we have a number of given accesses in this reference sequence here. The operating system has exactly 3 page frames, which is not a lot, obviously. And so you should simulate the replacement here. And you were also, you had space for also giving the control states for each of the memory frames, which might be helpful for implementing this algorithm here. So essentially, I think it's just useful to go through this again using the algorithm in the slides, because if I start explaining it here, well, it's pretty boring because I'm just reading numbers, and second, it really won't help you. So here it helps to go through it again and verify that you can actually reproduce the results here. So common errors here were mistakes when determining the age of a page or when using LRU because you didn't check the least recently thing, but something else. And of course, when you had partially correct solutions, so you made a mistake or two, you got partial credit for your solution as always. A bit more about memory. We had virtual memory, and first we had segmented memory. So we have the segment table here. So we have segment indexes from 0 to hexadecimal 1C. And for each of these segments, we have a start address also given in hexadecimal and the length given in hexadecimal. And then we were given two addresses here. So 0x0000 beef and 0x1CB00DA. And these were using memory segmentation. So we also set in the logical address the most significant 8 bits of the address indicate the position in the segment table, so which segment index it is. And you were supposed to determine the physical addresses from these logical addresses that use segmentation. So what you have to do is you have to look at the first 2 digits, hex digits, which is the most significant 8 bits of the number, and then look at the segment table. So you see it's the first address 0000 beef has the first 2 hex digits of 00, so it's segment table index 0, so the first one of our table. Then we see this actually starts at address E0, so it has an offset, and it has a given length of 2120FF. So the first thing you need to check is the offset in that segment, so BEF, actually still a valid address in that segment? Yes, it is. BEF is less than 2120FF. And then you need to add the start address of the segment to this logical address. So you have to calculate BEF plus 00000E0, and that comes out to 0000BFCF. The same happens to the other entry. So it's 1CEBODA, and 1C is our last entry in the segment table. So we also need to compare the segment lengths here. Now the segment length here is FFFFFF. So FFFFFF obviously has to fit because we only have 6 hex digits after our segment number. So we're also inside of our segment limit. And then we again have to add the start address of 10000 to this address here. So we have 1000 plus EB00DA, which is ECE00DA. And notice I used the underline characters here to always split our hex digits in groups of 4. That makes it much more readable. So these underlines are obviously not part of the hexadecimal number, but it just helps writing them. And I think it's actually allowed in very modern C dialects. And I think Go also allows it now just to make your code more readable when you have long binary or hex numbers. And they just can be ignored. As always, you get partial credit if you have a partially correct translation. You get no credit when you have a result without explanation. So if you only wrote the result 000BFCF here without showing me how you calculated it, sorry, no points for that. What were common errors? Well, hexadecimal addition is hard. We've seen some students actually converting all the addresses to decimal and then converting them back. That's painful. You shouldn't do this. You have an online exam, you have a hexadecimal calculator somewhere in your system. Please use it. You don't have to calculate it by hand, though our calculations you had to do were not that difficult. But still, I don't want to force you to compute that stuff in your head. So the second question was that about paging. So the same problem as before. So you have 2 virtual addresses and you were supposed to figure out the physical addresses. So here you would need to figure out where the page number is in your logical address and what the offset is. So we have 16 bits of addresses only, and we said that the 12 least significant bits are the offset inside of the page. So if a page size of 4 kilobytes, which in turn means that the remaining 4 bits, the 4 most significant bits, are our virtual page number. So what you have to do for these 2 addresses, OX6AB1 and OX41B7, is to first look up the page number, which is 6 in the first case, so the first hex digit here. And then, well, you have to look at the remaining offset, which is AB1. Now for virtual memory using paging, the offset always remains unchanged. So AB1 stays AB1. So the only thing that changes is the 4 most significant bits. And these 4 most significant bits, then you have to check. So you have to check the entry for page number 6, which has a start address of 0x4000. So it means we replace the page number 6 by 4, which is the page number of the physical page, and then we add the offset as before. So we just replace the first hexadecimal digit. So we have 4000 plus our offset AB1, which would result in 4AB1. And the same for F1B7. So we have to look at the last entry, OXF, which has a physical page at OX5000. So we end up at 5 plus our offset 1B7, which is 51B7. Again, partial credit if partial things were correct. No credits for just writing down the resulting address, because that would have been a bit too easy in an online exam, right? Common errors is that you just missed the line at the page number or did an incorrect lookup, or you actually added the start address to the whole 16-bit virtual address instead of removing the virtual page number first. So that's common errors that could show up here. And then we had a question which was a bit more tricky, and I admit that was a bit of an intentionally hard question. And we said in a system where we have a virtual address 722B2104, and this is mapped to a physical address 16A B2104. The question was, what is the largest page size that could be used for this mapping? So essentially, in other words, what is the largest page size that could exist in a computer system? So we could implement a mapping like this. And this was tricky because you are used to thinking that something always happens only on hexadecimal digits. Like you always have the leftmost hexadecimal digits, so 4 bits as a page number, but it could be an arbitrary number of bits. You don't need 12 bits as an offset. You could have an 11 or 13 or 21-bit offset, whatever, depending on the page size you want. And that's exactly what would happen here. And that's what you were supposed to find out. So the largest page size that could be used, that is actually the set of low order bits that are identical between the two addresses. Identical means 0 bits or 1 bits. So you have B2104 as the common suffix of both addresses. And that's what you would assume at first, right? B2104 are the last 5 hexadecimal digits here. But this would mean that it's 20 bits, right? But think a bit further. So the digit on the virtual address left to our B2104 is a 2, and the digit to the right of it is an A. So if you write them in binary, you notice 2 is 0010, whereas A is 1010. So we have 3 additional bits. These 3 additional bits in common could also be used. So we'd have a page size of 23 bits instead of 20 bits here. And that would still enable a translation like this. So this really was forcing you to think about what's happening here. Now, we know it was a hard question, and like half of the students really didn't have an idea of what was going on. But then we weren't that mean, so we only gave 2 points. And you should always think about, like, the number of points is approximately proportional to the time we expect you to work on that task. So if it's 2 points and you spend half an hour on this, you're doing something wrong, unless you have all the other points in your exam and still have half an hour left over. So that's the trick here. So partial credit for a correct explanation but incorrect result, but you didn't get credit for the result 2 to the power of 20 or a result without explanation. So these common additional 3 bits were the trick here, and that was tricky because that means, you really need to understand what was going on in virtual address translation. Then we had some typical scheduling tasks and expect a scheduling question on all operating systems exams. I don't think I have seen an operating systems exam that didn't have a scheduling question. So here we have three cyclically executing processes, 1, 2, 3, with some parameters like arrival times, CPU and IO times. And you always have these what we call bursts. So we have a CPU burst, so our process starts to compute, and then it needs to do some IO, so an IO burst, and CPU bursts and IO bursts alternate in our program execution. So what you were supposed to do is to fill in this Gantt chart here to enter the execution order and process state of all three processes for a scheduling algorithm that's using first come, first serve. And the important thing is that you needed to figure out, of course, some processes would be blocked, some would be ready waiting, and some others would be running. So a blocked process was doing IO, a ready process has finished IO or is just waiting to be started, but has not received the CPU yet, and the running process is the one currently running on the CPU. So this is referring to our very simple three-state process state model where we have running processes, we have block processes, and we have ready processes and the transitions between. So essentially the explanation is here. I don't think I need to read it, and that should be obvious. What's interesting is common mistakes. So the first common mistake is that the process was not considered periodic, so that students only gave one iteration for P1, 2, and 3. That made it a bit easier. Some students actually had problems counting, obviously, and some were actually assuming preemption, but FCFS is a non-preemptive scheduling. So a process runs to its end unless it's blocked, and then, of course, we have a process transition here. And then we had another scheduling with FCFS, with a number of processes, 8 processes here with arrival and burst times here, CPU burst times. And we have a Gantt diagram with a sequence and timing of process execution. And yeah, the question is, you were supposed to draw the Gantt diagram here and calculate what we call the average waiting time for 3 other scheduling algorithms. So we have given it here for FCFS, and we were expected to figure out the stuff for non-preemptive SJF, so shortest job first, preemptive round robin with a time slice of 6 milliseconds, and preemptive shortest remaining time first. So things we have discussed in the lecture about scheduling. So this gives the results. So the interesting thing is calculating the average waiting time, but we gave the formula in the question here. So if you had the numbers right, you just had to fill in the numbers in the formula and then get the average waiting time out there. So these are the Gantt diagrams here. Interesting again is common mistakes. So typically errors in calculating the sum or the average. If you made a small mistake like omitting a number or something, you got partial credits, or you just didn't read the question correctly because you used something else as a waiting time instead of what we indicated. Right. And then the final question was about all sorts of IO stuff, including disk scheduling and file systems. So the first question was again a piece of C code here that first allocated a buffer of 1 kilobyte, then did a memset of that buffer to 0 and did a seek on a file and read some stuff from a file. And you should assume that the file, which this file descriptor we pass to our read input function, refers to a file that contains the sequence of characters A, B, C, D, and that it points to the beginning. So the question asked was, which string does the buffer buff contain after the read call returns, assuming that no errors occur? So you needed to figure out what lseek did. So lseek positions your counter inside of a file. So lseek starts at the very first byte in a file, or the read or file access starts at the very first byte of a file. And lseek then sets, using seek set as parameter, the read pointer to the absolute position 3. Now remember, we always start a count at 0. So if we set it to 3, we skip A, B, and C. So the only character remaining is D. So L6 seeks the absolute byte position 3, reads the D, and the file only contains the given 4 characters. So a read temp of 1023 characters only returns the D, which is stored in the first byte of our buffer buff. That was not too difficult, I guess. So we're trying to read 1023 characters, but nevertheless, there was only 1 character left in the file. So we only got 1 written inside of our buffer. Common errors, well, 1 common error was off by 1. So assuming the file starts at an index of 1 instead of 0, well, then you're obviously off by 1 byte. Then there was another question related to that. What was the purpose of memset in the code above? And that clears the buffer pointed to by buff. And this is done to ensure that the string, if we read the string out of a buffer, it ends with a null or 0 byte. So we only read 1023 bytes. So we know that at least the last byte, whatever we read from that file, however large it is still a 0. So when we, for example, want to print the contents of that buffer, we always have a valid ending of a string here. Common errors was that the string needs to end with a 0, indicating a digit 0 instead of a byte value 0, which is of course incorrect and imprecise, or stating that the buffer is cleared. No, the contents, the buffer is cleared at the contents, not at the address, right? Yeah. What else do we have? Disk scheduling. So this is one typical disk scheduling question. This was a very simple one using FIFO. So you were given, essentially 3 read requests, L1, L2, L3. And initially, the first one is already known to the I/O scheduler. And the requests in L2 arrive after the first one was processed. And the requests in L3 arrive after more have been processed. So essentially, it's FIFO. It's absolutely simple. It's first in, first out. So it's just processed in the order we're giving here. That was a bit mean, yes, because many students were thinking too complex, like, what's going to happen here? Is this a trick question? No, it was absolutely simple. So maybe sometimes we err on doing things too simple and confuse you. We're trying to avoid this because that's not nice. Okay, and the final question was about file systems. So we had an inode-based file system, as shown in the picture here. So we have direct blocks and we have single and double indirect blocks. On a really Unix system, you would also have triple indirect blocks. We don't have any here. So the question we asked was to calculate the maximum possible file size using this double indirect scheme when we assume that a block is always 1024 bytes or a kilobyte, and a block number requires 4 bytes of storage. And then you should just give your calculation here. So the file size is essentially the block size times the number of blocks, which is a block size. And now you need to figure out the number of blocks. We have 10 direct blocks from 0 to 9. We have the number of single indirect block entries and the number of double indirect block entries. So we have 1024 bytes, which is our block size, times 10, which is the direct blocks, plus, well, we have 4 bytes for a block number, and we have a kilobyte size of a block. So we can store 256 block numbers in 1 kilobyte block. So we have 256 single indirect blocks, and we have 256 square double indirect blocks here. And if you calculate this, you get out a number of 67,381,248 bytes, or around 65.8 kilobytes, or 65,802 kilobytes, sorry, or about 64.3 megabytes, if we assume that we use 1024. So a megabyte is 1024 kilobytes. No matter which of these results you gave, so bytes, kilobytes, or megabytes, all forms of the results were counted as valid, but you needed to give the calculation here. And if you had simple calculation errors, you got partial credits. So one really common mistake is actually only assuming you had 9 direct blocks instead of 10. So that obviously, gave you 1 kilobyte to less. Another common mistake was assuming that double and triple indirect blocks would be there instead of single and double indirect blocks. So using squared and power of 3 instead of the just 256 and 256 square, which gave an enormous number. And that was the exam, I guess. I don't have any more slides. So I hope that wasn't too difficult. I hope that was about what you expected, I think. And that was the idea, to combine something from the lecture and the theoretical exercises with some of the experience from the practical exercises. So, for example, reading and understanding C code, using synchronization in our web server exercise between threads, using something like shell and building an internal shell command here. All of this is blended together here. So no matter what is your preference, I think you have always something where you might feel at home in the exam, and that's our idea we have. So assume that the complexity, the difficulty, and the amount of questions in the final exam will be similar. Of course, not identical, but we'll, if you look at types of question, of course, we'll have a scheduling question, we'll have a file system question, we have memory allocation questions, because these were the important topics, and go through all the stuff we mentioned at the Monday after before Easter. Really going through all the important points I mentioned in this slide set 2 weeks ago. And also just remember that there's some stuff we took out of the exam. So don't bother putting it in your head unless you're really interested, but you won't need it for the exam. That's, of course, a promise that we won't add any questions to the exam we told you would not be included. All right, I guess that's all from my side. Any questions? Okay. Everything's simple. Is it too simple? We can add a bit of complexity to the exam still. No panic reactions. Espen, what do you think? Was it too simple? Was it too difficult? Or was it okay? Some questions were tricky, yes.
Yeah, hello. Hi.
Hey.
Can you hear me? Yeah, I think there was a bit of a mixed bag. Like some of them seemed tricky. I wouldn't know the answer. Like I would have to look it up. But some of them I would be able, even though it's like 6 years ago since I took that course. So.
Yeah, of course. Yeah. Yes, of course. We have some trickier questions. Some stuff where you really need to think about it. You know, we unfortunately cannot give everyone an A, because then we'd end up at the title page of Universitätsavisa or Chrono, because our exam results are too good. And you know, that has happened before, though not in our department. And of course, we need to differentiate some. But I think from my experience, that's a relatively fair exam, though, of course, I have a bit of a different view on this. Yes, system calls questions required specific knowledge. Looking them up on main pages seems realistic. Yes, that's also expected, because this is an open book exam. You can use whatever you like, and we cannot control it anyways, because you're staying at home. And so you were supposed to read man pages before. And so if you're used to this, then you should know how to figure it out. Yes. But yeah, maybe we didn't give all of the details in the questions, but that I think is still fair enough, given that you have access to man pages. All right. So I guess I'm off for a beer. I stop recording first.